Hey guys, welcome to Pre-Calc, Lesson 5.2, Introduction to Matrices. Before we get to matrices, let's take a look at algebraic solutions again. Just a little warm-up here. So first thing I'd like you to do is number the equations, keep your work organized. And what I notice here right away is that I already know the value of z. It's going to make this so much easier because now I can take that and substitute it into this equation 2, and I just have a y left. So equation 2 becomes y minus a negative 2 equals 4. Obviously, those negatives cancel out. I'll subtract 2 from both sides, and I get y equals 2. Now what I'm going to do is take this value of y, plug it in here, that value of z, plug it in there, and solve equation 1 for x. So equation 1 becomes 2x plus y, which is 2, minus 3 times z, which is negative 2, equals 10. 2x, let's see, those cancel out. That gives me 6 and 2 plus 8 equals 10. 2x equals 2, so x equals 1. The coordinates of the ordered triple, that would be the point of intersection of those three planes, would be 1, 2, negative 2. Now, why was this system so easy? I want you to note the pattern. My top equation, I'm just going to rewrite 2x plus y minus 3z equals 10. The bottom equation, the middle equation, y minus z equals 4. And the bottom equation was just z equals negative 2. Well, notice what we had. In equation 2, we didn't have an x. In equation 3, we didn't have an x or a y. So this is the pattern I want you guys to notice. We're going to introduce matrices today. Notice how easy this is when these are zeros in here. We use what's called back substitution. I can take this value of z, plug it in here. That gives me y. Then I can take these two values and plug them in up above, and that'll give me x. All right, let's take a look at one more warm-up here. Solve the following three-variable system using Gaussian elimination. Now, that is a phrase that we're going to see quite often. Gaussian elimination. We really use that more with matrices than we do algebraically, but I'll show you how it works here. So equation 1, equation 2, equation 3. Right away, I notice it's probably going to be easiest to cancel the x's. I've got an x and a negative x, so first thing I would do is take these two equations, cancel the x's, and then probably 2 and 3. So let's do that. Equation 1, x plus 2y minus z equals 9. Equation 3, negative x minus y plus 2z equals negative 7. X's will drop out. 2y minus y is y. Negative z and a 2z is plus z. 9 minus 7 is 2. So that's a pretty simple equation right there. Okay, so again, you've got options here. I need to take two other equations, either 1 and 2 or 2 and 3. And it doesn't really matter. I'm probably going to take 2 and 3 because these numbers look pretty small. I just have to multiply this equation by 2. So I'll rewrite equation 2. 2x plus 4y plus 2z equals 14. And I'll take 2 times equation 3. Negative 2x minus 2y plus 4z equals negative 14. Okay, so what's going to happen here? X's cancel. 4y minus 2y is 2y. 2z plus 4z is 6z. And that gives me 0, which is totally fine. And if you notice, I can divide both of those by 2, so maybe I'll do that to make these numbers smaller. That gives me y plus 3z equals 0. That's going to be your equation 5. Now this is pretty straightforward. I need to take equation 4 and equation 5 and get one of the variables to cancel. Well, notice, that's a y, that's a y. So if I just negate this equation and combine it with that one, that'll work out nicely. So I'm going to take negative equation 5, negative y minus 3z equals 0. I'll combine those. Y's cancel. Z minus 3z is negative 2z, and that gives me a 2. So obviously z equals negative 1. I got that value for z. Now I have some choices. I can take that negative 1 for z, plug it in here, to find y, or plug it in there to find y. It doesn't matter. I don't care. To me, it looks like equation 4 might be a little bit easier to work with. So y plus z, which is -1, equals 2. I'm going to add 1 to both sides, so y equals 3. And now I'm going to take these two values and plug them in any equation you want. I'll probably go up top here. All right, so that's going to give me in equation 1, x plus 2 times y, which is 3, minus z, which is -1, equals 9. So those will cancel. This ends up being x plus 6 plus 1 is 7, equals 9. X equals 2. So the ordered triple is going to be 2, 3, -1. And it's probably one of the last times we're going to do algebraic solutions, because now we're going to introduce matrices. Let's talk about a matrix. What is a matrix? A matrix is simply a grid of numbers. It's going to look like this. I'm going to use some abbreviations. Row 1, column 1. Row 1, column 2. Row 1, column 3, ... Row 1, column n. Next, row 2, column 1. Row 2, column 2. Row 2, column 3, ... Row 2, column n. ... Row n, column 1. Row n, column 2. Row n, column 3. Row n, column n. Okay, so what do we have here? These are rows. And these are columns. All right, rows go like this, horizontal. Columns go like this, vertical. They're like pillars, columns. All right, so these numbers are just going to be in a grid, and each position can be denoted with a row and a column. So the order of a matrix simply means its dimensions. And the dimensions of a matrix are always row by column. We always mention the number of rows first. So you can see here, down below, a 2 by 2 matrix, which is super easy because we call it a square. That's why. Has 2 rows and 2 columns. All right, if I denote what those are, this would be row 1, that would be row 2, this would be column 1, that would be column 2. My next matrix, a 2 by 3, because it has 2 rows, row 1, row 2, and 3 columns, column 1, column 2, column 3. Remember, rows are horizontal, columns are vertical. And next I have a 4 by 2 because it has 4 rows. Row 1, row 2, row 3, row 4, and 2 columns, column 1, column 2. All right, so that's how you set up a matrix. How do we go from an algebraic system to a matrix? So sort of like we did with synthetic division, where we took that long division process and we eliminated all the variables and we just dealt with numbers. That's what we're going to be doing here. I've got a system of equations and I want to create a matrix for it. So there's 2 types, an augmented and a coefficient matrix. And for the most part, we're going to be dealing with augmented matrices. But basically, I need to represent this. Notice how it's sort of a grid already. That kind of looks like a row. And so does this. So my separate equations represent the rows. The variables represent the columns. So there's column 1, there's column 2, and then maybe this side of the equation could be column 3. That's all we do to set up an augmented matrix. Use the coefficients. Okay, so that matrix would look like this. 1, 2, 8, 3, -1, 4. Where this part of it represents the coefficients, 1, 2, 3, and -1. And this part of it represents the constants on the other side of the equals. Now notice, in order to go from here to here, we have to line up our variables, the equals, and the constants. So the coefficient matrix would just be those four coefficients, 1, 2, 3, -1. Now we're going to get into the mechanics of how we go from a matrix to the solution of the system. The first thing we're going to talk about is something called row echelon form, and that can be abbreviated REF. Row echelon form is simply a matrix that looks like this. And the dimensions can change, but you kind of get the idea here. This is what it would look like for a 3-variable system. So those are not hashtags. Those are just any random number. Those are just numbers, okay? But what do we notice here? Those are zeros. So if you go back to that first page of notes, we kind of wrote the equations out in this form. We notice, well, those are all zeros. But further, that's just an x, that's just a y, and that's just a z, all right? Those coefficients are 1. So what we know, if I can get a matrix like this, is that value right there, z equals whatever number that is. That gives me z, because remember how this is set up. This is x, that's y, that's z, and that's our constant on the other side of the equals. This represents equation 1, that represents equation 2, and this represents equation 3. So by getting it in this form, I start by knowing what z is, then I can plug that number in here for the z, and then I can get y, and then I plug both of those in here and here, and then I can get x. All right, well, Gaussian elimination, we heard that in the first page, is simply the process used to get a matrix into row echelon form. So the formal definition for Gaussian elimination is using elementary row operations to get a matrix into REF, row echelon form. So that doesn't mean a whole lot to you guys because you don't know what the elementary row operations are. There's only 3 of them. It's not too bad. First, given a matrix, you can switch any 2 rows. You just interchange them. Simple. Next, you can multiply any row by what's called a scalar. And a scalar is simply a non-zero number. So you can't multiply the equation by 0 because that just eliminates it. But 1, -1, 7, 3, whatever number you want other than 0. And then lastly, combine any 2 rows and replace one of them. So let's say you combine rows 1 and 2. You would then have to replace either row 1 or row 2. So you combine the rows and then you replace one of them. Your choice, which one you want to replace. Now we're going to solve a system using Gaussian elimination on a matrix and then back substituting. First thing I need to do is create a matrix from this equation right here, or this system of equations, I should say. Well, that's not too hard. That's the easy part. It helps if you write small. So we're going to be writing a few of these. First row is going to be 3, -4, -4. The second row is going to be 1, 2, and 10. Now, before I do any work on that matrix, I need to understand what my goal is. My goal, if I'm using Gaussian elimination, is to make this matrix here look like the following. 1, number, number, 0, 1, number. There's a certain pattern you guys are going to realize here when we do these, and this is a simple one because it's only a 2-variable. We're going to go up to 3-variable by hand. Is what do you do first? And this is the confusing part. It's like a geometry proof. All right, there's more than one way to do it, but there's a most efficient way to do it, which is probably in your best interest. The first thing you always try to do is get a 1 in row 1, column 1. So I need to get a 1 here. I need this to be a 1. Well, remember, we're going to be using our elementary row operations. I see a 1 here. Well, I don't want it there. I want it here. Remember the first thing you can do. Switch any two rows. So I'm going to switch these two rows, interchange them. So what I do to show the work, and what you need to do, is you're going to create another matrix right underneath, and you're going to indicate to me what you're doing. So what we are doing is we're taking row 1, double arrow, row 2. That means interchanging those two rows. So that bottom row is going to go up top. 1, 2, 10, and the top row down below. 3, -4, -4. Okay, so now, got it. Great. I got a 1 in that position right there. So the second thing we do is we get a 0 here. We use this 1 to get a 0 there. So that's going to be second. So how can I use this to make that a 0? Remember our other two row operations. Multiply any row by a scalar. So I can pick any number I want other than 0 and multiply this. Well, I bet -3 would be a good choice. And I'm going to combine it with that third row. So now here's what you're going to show for work. That top row is going to stay. 1, 2, 10. I'm not going to change that because if you notice here, 1, 2, 10 fits this pattern. 1, number, number. This is great. I'm not going to change that. I need to get this to be a 0. And I need to get this to be a 1. So the first thing I'm doing is making this a 0. How are we going to do that? I'm going to take -3 times row 1 and add it to row 2. And I'm doing that work right here. -3 times this plus that. Okay, well, -3 times 1 is -3 plus 3. That gets me the 0. -3 times this is -6 minus 4 is -10. -3 times that is -30 minus 4 is -34. All right, so now, once I've gotten a 1 here and a 0 there, which I have, now I get this. That is always done third, if it's a two-variable system. And now, I'm going to do this. Now, a scalar doesn't have to be an integer. It can be a fraction. So basically what I'm doing here is I need to multiply this row by something so that this becomes a 1. So think of it this way. -10 times what equals 1? -1/10. All right, so basically it's division, but technically you have to turn it into multiplication. All right, so last matrix here, the top row stays 1, 2, 10. And what I'm going to do here, notice I'm writing down what I'm doing right next to the row. So what I'm going to do here is take -1/10 R2. Take this row, multiply it by -1/10. Well, that's going to stay 0. That's going to become a 1. And basically, I'm dividing this by -10, so it's going to become 3.4. So 0, 1, 3.4. So now, if you notice, this matrix is in this form. I've got everything I want. What does it now tell me? Well, it tells me this the bottom row, I should say, tells me y equals 3.4. So remember how this works. Here's your x, here's your y, and there's your number. So in this equation, I have 0x plus 1y equals 3.4. That's why I do it. Now this equation is x plus 2y equals 10. X plus 2y equals 10, and then use back substitution, right? I know that goes in there. X plus 2 times 3.4 equals 10. X plus, this is easy to do in your head, 6.8 equals 10. I'm going to subtract 6.8 from both sides. X equals 3.2. So there's my solution. Basically what I've done is I found the ordered pair, 3.2, 3.4. There are only two variables in this system, so this represents a linear system. Two lines intersect, and there's your point of intersection. Example 2. Solve this using Gaussian elimination. So again, I want to put this into a matrix. First row, 3, -5, 18. Second row, -6, 10, and 20. Now, as a visual again, my goal, 1, number, number, 0, 1, number. And always get a 1 there first. Well, I'm going to caution you about something. I don't see a 1 in either one of those, so I can't flip-flop. It won't do me any good. I can't multiply this by anything to make it a 5, and I can't multiply this by anything to make that a 2, so when I combine them, I get a 1. It's not going to work. So I could theoretically multiply this row by 1/3. That would give me a 1 there. However, that would be negative 5/3, and that would be a 6. So while that's possible, I'm going to have to use negative 5/3 then to work with the other equation, and that's just going to be a pain. So my recommendation is to, I'll put a little asterisk there, never divide first, unless they will be integers. So for example, if this was a 6, yeah, I would definitely divide everything by 3. But I don't want to divide by 3 if I'm going to be left with a fraction. So if I can't get this to be a 1 first, skip it, and let's still get that to be a 0 second. So I'm going to skip trying to get this to be a 1, but I'm going to make this a 0. All right, how am I going to do that? Well, I'm going to multiply this by 2 and add it to that. All right, so my top row stays for now, 3, negative 5, 18. Now I'm going to take 2r1 plus r2. I'm doing that here. 2 times this, 2 times that, plus 6. Well, that's going to be a 0. 2 times negative 5 is negative 10 plus 10. That's going to be a 0. 2 times 18 is 36 plus 20. That's 56. Well, we just solved this, sort of. This is saying 0x plus 0y equals 56, or 0 equals 56. Well, remember from yesterday, that means no solution. If you get down to a false statement, there is no solution. So 0 equals a number means that there is no solution for this system. 0 equals 0. Infinite solutions, then we have to go on a little bit further. But for this example, we are now done. All right, the last one, the biggie, moving up to a 3-variable, 3-equation system. First thing we're going to do is write the matrix and write small. Top row, 1, negative 2, 3, 9. Middle row, negative 1, 3. Be very careful here. There's no z term, so I have to fill in with a 0. And negative 4. The bottom, 2, negative 5, 5, 17. So for this one, this is super important. This is the hardest one. My goal is going to be 1, number, 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 0, 1, number, number, 0, 0, 1, number. And follow the pattern. First, get a 1 there. Excellent. Already done. Great. Second, get this 0. Okay, so in order for this to be a 0, I notice if I combine it with this, that would give me a 0 there. So I'm going to write my new matrix. Like I said, we're going to be writing lots of matrices, so just get used to it. And what I'm going to do is I'm going to take R1 plus R2. I'm just going to take these 2 rows and combine them and put that in row 2. All right, so I'll add those, that's a 0, add those, that's a 1, add those, that's a 3, add those, that's a 5. That's how I get these values. 0, 1, 3, 5. Okay, my bottom row I didn't touch, so that says 2, negative 5, 5, 17. So now, back over to my goal. Third, get that to be a 0. So now, as I look at this matrix, I want this to be a 0. Well, one of the reasons why we like to get a 1 here first is because now I can use this 1 to get that to be a 0. I'm going to multiply this by negative 2 and add it to that. Okay, so my matrix, top row stays the same, 1, -2, 3, 9. Middle row stays the same, 0, 1, 3, 5. But what am I doing now? I'm going to take -2R1 plus R3. So I'm going to multiply this row times -2, combine it with this row, and put that right here in row 3. All right, so let's be careful when we do this. -2 times 2 plus 2, that's a 0. -2 times -2 is 4, plus a -5 is -1. -2 times 3 is -6, plus 5, that's also -1. -2 times 9 is -18, times, or plus 17, sorry, is -1. All right, so now, next, my goal. Fourth, get this to be a 1. Look at your matrix. That's already a 1. And again, the reason why I want to get this to be a 1 first is because now I'm going to use this to make that a 0. So fifth, it's going to be that right there. Well, look at what happens. I'm going to use this to make that a 0. So I'm just going to take row 2 plus row 3, and then that'll drop out. Okay, so my next matrix, top row stays the same, 1, -2, 3, 9. Middle row is going to stay, 0, 1, 3, 5. So now what I'm going to do is I'm going to take row 2 plus row 3. I'm just going to combine these two rows right here and put that in this row 3. Okay, so 0 and 0 is 0, 1 and -1 is 0, 3 minus 1 is 2, 5 minus 1 is 4. So now you have no choice. Once you've got these to be zeros here, you've got no choice but to use division here. Division should be the last thing you do. So no matter what number you have here, if it's a 7, if it's a -3, you have to divide. That's going to be the 6th thing we get. So hopefully I have room down here. Yeah, I do for one more. Perfect. So my last matrix, top row, 1, -2, 3, 9. Middle row, 0, 1, 3, 5. What I'm simply going to do here is take 1/2 of R3. I'm going to take this row here, multiply each thing by 1/2. Okay, so it's 0, 0, 1, 2. Awesome. Now I'm done with the matrix because I have row echelon form. Look, I've got these zeros here, and I've got ones here, here, and here. So now I'm going to use back substitution because what I know, once you get to this, is that z equals 2. All right, so if z equals 2, I'm going to take this equation, which is y plus 3z equals 5, and I'm just going to plug in a 2. Y plus 3 times 2 equals 5. I'm going to subtract 6 from both sides. Y equals -1. Awesome. And now lastly, I'm going to take this equation, which is x minus 2y plus 3z equals 9. And I'm going to plug in 2 for the z and -1 for the y and solve that. X minus 2 times -1 plus 3 times 2 equals 9. So right here, those cancel. That's going to give me x plus 2 plus 6 equals 9. Subtract 8 from both sides. X equals 1. So the solution to this system as an order triple would be 1, comma, -1, comma, 2. Whew. That's about as tough a question as you're going to see. You will actually have a quiz that is very similar to this, a 3-variable, 3-equation system that you have to solve using matrices. So thanks for hanging in there, guys. As usual, if you have any questions, don't hesitate to reach out, and we'll see you in class soon.